Given 3 points in the plane,
Yeah.
can you always draw a circle through them?
Yes.
Yes. Yes.
No! No! They're all in a straight line.
Are you done yelling at me yet?
Sorry.
So,
They're not on this.
if you have 3 points that are not on a line,
Okay. Yes.
Yes.
I think that's
I think so. I don't know. Let's
I don't know if it's.
That's all. Yes.
And you're done.
Let's say yes.
I think it might.
given 3 non-collinear points in the plane,
I think you can.
I think you can.
My intuition says yes.
does there exist a circle
It could be
passing
an
through
infinite circle, and therefore it could be on the same line.
them all? Are we, well, the noise level has subsided. What's the answer?
Yes.
How many such circles?
One.
So you're alleging it's unique?
Yes.
Yeah.
All right, so in fact, you guys might recognize this as a classic question about triangles. If you have 3 non-collinear points, they form the vertices of a triangle. There is something called a, not inscribed, circumscribed circle. Circumscribed circle is in fact, well, that's not looking very circle-ish. Is in fact the circle, now I'll do better if I actually, how do you find where the center of said circle would be? It has to be a point that's equidistant from all the vertices. So how do you construct it geometrically?
Is that
It's perpendicular bisectors.
I see.
And one of the problems that was a challenge problem the second week of school that well, Allison may have done this one, was to show that if you take the perpendicular bisectors, all 3 of them go through this point of intersection.
I did do that.
Okay, you did do that one. So that's the center of the circumcircle, hereby known as the circumcenter. So those distances are all the same, and there's a unique circle, and we constructed the center of it. But we're doing linear algebra. Yeah, right. Who knows what a triangle is? So, how would we do this? Linear algebra. And you will have a similar problem on your homework next week, a related problem next week. Well, what's the equation of a circle? Well, but the circle is not likely to be centered at the origin. So here's what I want. So given 3 points, P sub I, which I'll call xi, yi, so I have 3 points in the plane. I want a circle that's going to go through them all. How do we find a circle that's passing through all of them?
We can find the center of the circle by finding one point that's equidistant from all 3, and then draw a circle with radius of the distance to each.
So you're looking for the circle, but that's sounding like it's not, yeah, that's going to be harder, I think, actually. So I was asking you guys what the equation of a circle was. And Alex told me a circle centered at the origin. Can you give me a general circle?
X minus 6 minus r squared.
Okay.
The distance between each point and the center is r.
Correct. Now the trouble with this equation is, what does it mean to say, so you have three unknowns here, right? The center of the circle and the radius. Well, we don't know it. There's three unknowns,
For
right?
all the, for all the points to satisfy, to the line of the circle, they have to satisfy that equation.
So I have to be able to plug in each of these points pi into this equation. So for example, you could think of this as a function of x and y, and you were saying that if I plug in p1,
You got three
actually
equations,
I'll
three
actually do
unknowns.
this.
Actually.
I'll subtract the r squared and say, when I plug in all the points, I should get 0.
And that's three equations and three
It's
unknowns.
three equations in
Three unknowns.
three unknowns. However, they don't look like linear equations to me.
Uh-oh.
A, B, and R don't look like they're appearing linearly.
Make them.
Would you all agree with that?
Yeah.
So sadly, this is a system
S.
of three quadratic equations in A, B, and R. I want linear equations.
Let's make them.
Thank you, Mr. Salmon. How do I do it?
It's not square both sides.
So notice that if I expand this out, what does it look like? It looks like x squared So this part's linear in A, this part's linear in B.
The a squareds are going to cancel out, right?
Hmm?
When you have all of them, you can cancel them out.
If I take two equations and subtract them, you're saying,
Yeah.
then the a squareds and the b squareds and the r squareds will cancel. But I still,
Oh, but then yeah.
so how about we rewrite this way? How about we say new variables, capital A, capital B, capital C, where capital A is minus 2 little a, capital B is minus 2 little b, and capital C is a squared plus b squared minus r squared. So this is, I'm doing what Dan wanted me to do. I'm making it into a linear equation in the variables by deciding to use different variables. So now my equation becomes x squared plus y squared. Remember, x and y aren't my unknowns. They're the variables that I'm going to substitute in my points for, so those will become numbers. Plus ax plus by plus c equals 0. Does this look more linear in my variables? In other words, this actually becomes ax plus by plus c equals the negative of x squared plus y squared. And now, plug in the points P1, P2, P3, this becomes a system of linear equations, right? If I put in the points, I'll get a times the x-coordinate of P1 plus b times the y-coordinate of P1 plus c equals a certain number, namely that. You guys buy this?
Isn't that just extra notation for convenience?
Extra notation for?
Convenience. Doing the capital A, capital B, and capital C.
Well, I'm trying to make you realize that we can, by looking at different variables, that we have a system of linear equations. What do you want me to do without
If you
making that notation?
just did the rearranging, it would still then be. I retract my question.
I mean, but you have to recognize that these combinations
Right.
are your new variables. Okay, do you all agree that I now have this system when I plug in the points, and it is in fact a linear system in A, B, and C? All right, so now your task is to tell me whether this system of three linear equations in the three unknowns, capital A, capital B, capital C, has a unique solution, no matter what the 3 points are, just knowing that they're not on a line. So now, it is slightly unfortunate that I used the letter capital A, because I can't now use that to be a matrix. Slightly inconvenient. What's another good letter for a matrix?
G. Let's use I.
Can't use A, B, or C.
Let's do Z.
Confuse everybody.
Z. Upsilon?
It's like an accident. The accident.
Capital C. What's my matrix of coefficients?
Wait, what? What's that?
No, A, B, C are my variables.
X1, B1, or yeah, X1, Y1, 1.
That continues.
Agreed? That's my matrix of coefficients for those linear equations. And then the right-hand side, the vector is the minus the sum of the squares, right? So, from what we talked about in class yesterday, what do you want to know about this matrix capital C if you want to claim that there's a unique solution to this system of equations?
We want to do.
You want to know capital C is non-singular. So, let's method of wishful thinking. Claim capital C is non-singular. Then, no matter what right-hand side I have, there's a unique solution. There's your unique circle, because if you have a unique capital A, capital B, capital C, you now know the center of the circle and the radius. Agreed? So why in the world is this matrix non-singular?
Because none of the points are in the same line, so you won't end up with a free variable. So, because if they land in the same line, they'd be,
You'd have an extraneous.
So you want to claim what you believed is that C is singular if and only if the 3 points are collinear. Now, in fact, which direction do I need to prove here? If I want to prove that if the 3 points are not collinear, then the matrix is non-singular. So not collinear implies not singular, that's that, right? Right? The contrapositive of this would be non-collinear points implies non-singular matrix.
Okay.
So what does it mean? So we could try to be a little less abstract here and just fiddle with this matrix. Is there something else you wished we could do with this matrix? No, we don't know that. But I heard you. Wouldn't you wish that the ones were somewhere else?
Let's put them at the front.
Now that you say so.
Where would you wish they were?
No, in the front.
In front, namely, you wished we could switch the columns, right? Now, we're not allowed to do column operations, although we'll do that at one point next semester. Equal opportunity, you know.
Yeah, doesn't it really matter?
That's the
Yeah.
point. So Alex is exactly making the right observation. Rearrange the variables. If you put the C in the front, you could call up.
Okay.
That would have been good for Tim in the rain. Now the ones go in the front, and now it looks more like it's susceptible to our usual sorts of algorithms. So just by reordering my variables, I could instead consider this matrix, capital C prime, which does not stand for derivative. So let's see. If I start with this matrix, and I use our algorithms to put it in echelon form, what do I get? Copy the first row.
And 0. x2 minus x1. y2 minus y1. 0. x3 minus x1. y3 minus y1.
Now, I don't want to go any further. I now want to use my brain.
How would this be?
If the bottom,
Collinear, the bottom two rows can't be multiple of one another.
Right. The bottom two rows are multiples of each other if and only if,
yeah,
what are we saying? We're saying some multiple of this row would equal this row. But look at that geometrically. Think about transposing it. We're looking at a vector that goes from P1 to P2. That would be the vector whose components are these two numbers. And what would it mean to say some scalar multiple of that was this vector? Right, so transposing, we see that the last two rows are parallel as vectors. If and only if the vector from P1 to P2 is parallel to the vector from P1 to P3. And that's saying the 3 points are collinear. So the matrix is non-singular, so there's a unique circle. End of story. Got it? So you will have a variant of this to do in homework next week for parabolas. And the cool thing about my being mean to you is I don't know a geometric construction to construct a parabola through 3 points the way I know a geometric construction to construct a circle through 3 points.
So we keep going and solve it.
No, I'm not going to keep going and solve it.
But we could.
If you had, I believe you have a web work problem to do it with numerical data.
Okay.
Okay? So there are all sorts of variants of this that you can do if you become more sophisticated mathematicians. For example, given 5 points in the plane,
You can draw a pentagon.
no 4 of which are collinear, I believe, but 3 could be, but no 4 of which are collinear, there's a unique conic through the 5 points. So,
I feel like
so you can do that. You can do that by the exact same linear algebra. You just have to have more variables. Okay. Any other questions? Guess I can put that down as a challenge to you.
Oh, man.
Prove that 5 points.
Show that 5 points.
Geometrically or algebraic?
Algebraically is what I have in mind. 5 points always lie on a conic. If you allow the case of 2 lines, so conic is just something that's given by a quadratic equation. And so you have ellipses, parabolas, hyperbolas, circles are a special case of ellipses. You also do have 2 lines as a special case. If you allow the case of 2 lines, it will be unique whenever no 4 points are collinear. So even if 3 points are collinear, and the other 2 obviously are collinear, you'll have 2 lines, which is a special case of a conic. You can slice a cone so that you get 2 lines. Now you're going to complain at me that if this line were parallel to that, you wouldn't know how to slice a cone to make that. But if you do projective geometry, it's all the same. So anyway, I'm not going there. Okay. So I promised you, before we go on to the next section, I promised you a discussion of having the other chalk drop. Reduced echelon form, ref, is unique. In particular, along the way, we'll prove that rank is well defined. Any 2 echelon forms of a matrix have the same number of non-zero rows. So that'll be my first step. Okay, so most people don't stop to do a proof of this, and I often don't, but you guys are special, so you deserve it. It's actually not that bad a proof. So it's the proof is based on understanding our algorithm for reading off the general solution. Remember how you've been doing that in your homework? You even had a little on web work, but you also have more to do in book work, right? So once you get the pivots, you solve for the pivot variables in terms of the free variables, and then you create the vector of solutions. So if you understand that algorithm, that's what we're going to use here. So we're going to start with a matrix A, and we're going to suppose that B and C are 2 different echelon forms, for starters. Okay, so it's the first step I'm going to do is just working with echelon form, and then I'll get to reduced in a minute. So how do you show that these two matrices have the same number of non-zero rows? What would
We have the
be?
same rank.
I'm trying to prove rank is the same. What would you say would be a standard math technique to show the two things had to be the same?
Pretend they're different.
Pretend that they're different.
Standard procedure.
So suppose that B and C have different numbers of non-zero rows. What does that mean in particular has to be true? So here's B, here's C, and let's say that the different numbers of non-zero rows. So which way do I want to do this? Well then C, let's say C has at least one more row of zeros than B. So B might have a row of zeros here, but C outdoes it and has at least two rows of zeros. What does that mean has to happen?
C has to have one more free variable.
Which is the same as saying B has to have one more pivot. So there's at least one, but all we care about really, one pivot variable, let's say xj, for B, that is what for C?
It's a free variable.
Do you agree with that statement?
Yeah.
There has to be at least one more pivot here. And therefore, there must be some pivot here that isn't a pivot there. Because otherwise, there'd be just as many pivots here as there were there, and we already said that can't happen. You buy that?
Yeah.
So what does that mean? That means in the jth column here, somewhere along here, there's a 1, where there is no pivot in the jth column here.
I thought we were working with just general echelon
Yes.
form. Could it be any number?
Oh, sorry.
There's a non-zero.
Fair. Absolutely. Star. But not 0.
Star.
And now what's true if that's a pivot? Then there's all zeros below there. And if it's not a pivot here, there can be numbers in the jth column, but there can't be a leading, right? So what if this is a pivot, there's echelon form is cleared below, but there's also zeros here, right? Whatever row this is in, there's zeros up to that, but there's no pivot in the jth column here. You okay so far? So what does it mean that there's not a pivot in the jth column here? It means, if you think about your algorithm, that j is a free variable. I already said that, right? xj is a free variable for C. Now you know from our algorithm These aren't in reduced form, but even so, you know that therefore there is a vector that has a 1 in the jth slot and zeros everywhere after it.
It's a star.
Star just means not zero, or arbitrary. All right, so let's just say blah. Arbitrary entries there. So there is a vector with a 1 in the jth slot that we're thinking of as coming from putting this in reduced echelon form, getting a 1 for all the pivots, and then for each free variable you get a vector of in your general solution. Right? Remember, each time you've done the general solution, you get a vector for each free variable. So that it solves the equation. So remember, when we've done our algorithm, you get a 1 in the free variable slot, and then you have zeros after that. If you look at all the examples you've done, when you've solved for the general solution, once you have the free variable, the previous variables might depend on it, but the subsequent ones never do. So go back and look at your examples that you've done. But then I'm done, because look, this is a vector that solves Cx equals 0, but can b times x equals 0?
No.
Remember, this was a pivot back in the B matrix. So let's say this is the nth row of B. What do I get when I take the nth row of B and multiply it by x? So the nth row of B had zeros up until this non-zero thing, which was in the jth slot.
Right.
And it had junk here. And what do I know about x? It's got junk, 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 junk.
It's got a 1.
And it's got a 1 in the jth slot. And then it's got zeros everywhere after it.
So it's got a non-zero.
It's gonna be star.
What happens when you multiply these? You get star, which isn't 0.
It isn't.
Right? When you do da-dum, 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 then you get 1 times star and then 0 of all those. So the nth row of B is not orthogonal to x. So therefore b times x can't be 0, because the nth entry of this would be this number. So what does that mean? It means that if we had an extra pivot in B, we would have some vector that solved Cx equals 0 but doesn't solve Bx equals 0. Why is that impossible?
Because they should have the same solution.
Right? What we argued at the very beginning when I started this stuff is when you do row operations, you don't change solutions. But remember, if B and C are echelon forms of A, any vector satisfying Cx equals 0 satisfies Ax equals 0, and thence, since B is also an echelon form, Bx equals 0. That's a contradiction. Oops. All right, so they have to have pivots in the same places. Must they actually, so they have to have the same pivot variables. So any two So now I'm going to do the second part of the proof. Any two reduced echelon forms must therefore have the same pivot variables. Must the pivots actually be in the identical spots in the matrix? Suppose x2 were a pivot for B, and it were also a pivot for C. Could they appear in different rows?
If you did row echelon, don't you have to move it so that it becomes an echelon form?
You switch rows, right? So that
Yeah, so that it works like that x2 would have a pivot variable in the second row. Like that's how you create the echelon form.
well, it could be in the first row. You could have a pivot in the first row, provided there was no pivot in the first column.
Yeah.
But that has to be true for C as well. Because if x1 is not a pivot for B, it can't be a pivot for C. So therefore, C would likewise have to have x2 as its first pivot. And it would have to be in the same row. If at any stage the rows didn't agree, that would have to mean that you were a pivot off, a pivot variable off between the two matrices before that point. Think about this as writing a computer program instead. Ask yourself, is x1 a pivot variable? If so, both matrices have a 1 there.
Well, just echelon forms.
No, I'm doing reduced now. So ask yourself, is x2 a pivot variable? If yes, then they're both appearing there. If no, neither of them has a pivot in the second column. So you go to x3 and ask, is x3 a pivot? They have to agree or disagree, both of them. So you're going to end up constructively saying that your pivots have to be not only in the same columns, but also in the same rows. Well, I'm not done yet. Okay, but I'm saying they must have the same pivot variables, and then it follows that they must be in the same positions. You just basically argued that if they appeared in different rows, if the pivot appeared in different rows, you'd be a pivot off somewhere before that. All right, so now the only question is why, if you have non-pivot stuff, so suppose you have reduced echelon form like this, and I'm just going to be, for convenience, I'm just going to assume that I haven't skipped any columns, just for convenience. This is not I'm not using it in the proof. But suppose B and C start off with the 1s in the same places and the 0s in the same places so far. And then suppose there were some number over here that disagreed with the corresponding number over here. It doesn't look quite right. So suppose all the pivots are the same. And some Bij is different from Cij. Do you now see what's wrong? So here I am in the ith row here, and the jth column here, and the ith row here, jth column here, and the numbers are different. I mean, think about this. Think about the ith row. When you do your algorithm, when you write down your ith pivot variable in terms of all the free variables. I'm assuming it's a homogeneous equation. I'm ignoring the right-hand side if they were inhomogeneous. So what would you have here? Well, xj is one of the free variables. So I have various junk with various free variables. And then I would get a minus bij xj, right, when I solve for xi and move the other stuff to the other side. And I'd have other stuff. But it would also, from the matrix C, I would get the corresponding equation, xi is junk minus cij xj, and junk. The junk may or may not be the same, but this is already enough to cause me trouble. What are you going to do now to see we have a problem? All these terms involve various free variables. What can you do with the free variables? You can make them be anything you want. That's what free means.
So make them equal.
So what should I do? Set xj equal to
0. 1.
1, and all the other free variables.
0.
So what happens if you make xj to be 1 and all the other free variables to be 0?
Yeah.
You get.
Xi
We get that.
So if we set xj equal to 1 and all other free variables equal to 0, we get xi is 2 different numbers. But the solution's supposed to be unique, right? If you have a system of linear equations, you know what a solution would be. Its ith coordinate can't be 2 different things. So the fact that the original equation can't have a solution x with well, so what am I doing here?
You're not throwing it at B and C.
Oh yeah, so the point is, yeah. So if x is a solution of ax equals 0, it must solve bx equals 0 and cx equals 0. Well, putting this particular value of xi in, it can't be different in these 2 different cases. Because it has to be, whatever vector I have that works for A has to work for both B and C. So if I take B times the vector that works for C, that means I'm going to have something like zeros, okay, yeah, so I think what I wanted to do, I didn't think through this part carefully. What I wanted to do is actually take the highest position that disagreement could occur. So I want to assume that everything in the matrix is agreeing up to that row. Yeah, okay, so I'm not going to finish the argument because I've flubbed it here. So finish the argument by choosing I and j so that all other entries above the same. And same on the ith row up to j. And then you're going to see that you can't have a solution with these different. Okay. So I'm hand-waving a little bit at the end. It takes a little bit more refined argument that I am prepared to make in -1 minute. So I'm going to say that's the idea of the proof, and I didn't quite finish it. One demerit to me. All right, so next time we're going to start talking about, tomorrow we're going to start talking about inverse matrices and connect it to what we've been talking about with non-singular matrices. So on to section 2 tomorrow.